Alright, so let's get started. And the slides is also available on our course website. If you would like, you can download it on your own laptop. And today I'm going to talk about a topic in computer vision, that is image classification. So let's talk about the problem definition. So image classification is for us very intuitive and straightforward. Given an image, we want to know, okay, if there are several classes predefined, which class the image should belong to. But however, technically, it is very challenging because, as you can say, when we see image, what does this mean? It means a type of data. What kind of data? It's a very high dimensional data. Say, for a small image, for the 100 pixel by 100 pixel times 3 channels, if it is colorful image, then what is dimension of the image? It is 100 times 100 times 3. So it is 30K. It is quite a high dimensional data. Okay. So if you are familiar with some computer machine learning dataset, for example, the iris dataset, how many dimensions are in the dataset? In fact, only 4. So compare with 4 and 30 K. So you can see one is low dimensional data and one is high dimensional data. So that's the problem of image classification. And in addition, for some images, they belong, if their image resolutions are different, then they belong to different image data spaces. And it will be another challenge for image classification. So this is table showing some image classification data sets, and we will go through all of them. And you can see in the very beginning, 1998, there is a MIST. Okay, this is a very famous data set. There are only 10 classes. And okay, so for in 2006, the class is only 10, and the Pascal VOC, the classes increased to 20. And okay, there is a very impressive dataset called ImageNet. There are 21K classes. It's a huge increasement. And there is a challenge from 2010 to 2017. It means Image Large Scale Visual Recognition Challenge. They only select 1,000 classes from the 21K classes, so that they can use it as a benchmark to test or to encourage researchers to develop the new, more effective image classification algorithms, and we will see them there. Okay, and after the challenge ending in 2017, there are some more new dataset was released. For example, Fashion MIST or Med MIST. Some of them are medical, or some of you are medical, are interested in medical images. The Med MIST will be a, I should say, it is like the MIST for computer vision, and the Med MIST is the simple, I should say, small scale, small size images for medical researchers. Okay, so let's go through that. So what is MIST? The full name of MIST is Modified National Institute of Standards and Technology. So what does it mean? That is the American Institute for their standard. So this is Institute of Standard. Okay. And so as this dataset was released from here almost 26 years ago. Okay, so 26 years ago, what they will collect is the handwritten digital digits. They collect those digits from checks and from the envelope, because we will write some zip codes on the envelope. Okay, so let's see their scale. There are, of course, because there are 10 digits, so there are 10 classes, and there are totally 70K digits, and the resolution is not large, only 28 by 28. Okay, let's see the next. Okay, in 2006, some researchers want to class images for natural things, so they collect. So Xerox is the very famous paper copying enterprise. They compile a dataset. The dataset is not very big from our perspective now, but in say several 18 years ago, it is still okay, an interesting dataset. So here, this is the first problem. There are different resolution from small image to large image. How to classify images from different resolution? This will be first challenge. Okay, so we can see some examples here. There are only 10 classes, and in every class, those example images contain the object. So this is bike, book, chair, and the phones. And in the following slide, we will see a method addressing the problem. How to classify images on different resolution. Okay, then there was the Pascal VOC dataset. So VOC means Visual Object Classes. And this is a challenge hosting from 2005 to 2012. So as you can see, in the beginning, there are only 4 classes, and there are only 1,500 images. And then in the next year, they increases the number of classes to 10, and one more year to 20. And also, there are more images added into the challenge. So it's become more and more challenging year by year. And they not only do the classification task, there are also other visual related tasks. For example, detection. Detection means given the image, yes, I know this is the image of chair classes, but where is the chair? Detection means they want to localize the object in the image. So you can see there is a yellow bounding box show the location of the chair, the bike, the boat, and the cat and the dog. So you can see sometimes the bounding box overlaps because this is a cat, it is braced by a dog. Okay? So this is the first task. And the second is segmentation. Segmentation means, okay, given an image, or there are some chairs on the image, they want not only localize the location of the chair, they want to know pixel by pixel which pixel belongs to the chair and which pixel belongs to the background. So you can see this is they can, okay, let me enlarge it. Okay, they can segment, the ideal case is segment the chair from the background. And what's the difference between the two images? The two images, okay, from the left hand side, it means instance segmentation. It means the 4 chairs are viewed differently. Okay, so you can see their color. There is blue, yellow, green, and purple. They use different color to label the 4 chairs. And this is more semantic segmentation. It means they only care whether this is a chair or not. Okay, if they are chairs, they all they try to segment that without considering this is first chair, second chair, or third chair. And there are two more additional tasks. It is let's see, action classification. So you can see there are many human objects and they are doing something. So let's enlarge the label. You can see, okay. So they are running, and this is riding horse, and this is playing instrument. So this is an action recognition task from images with human. And then the last one is the person layout. It means given an image, if there are some person on the image, then they want to localize the human part, face, hand, and okay, there are some foot. Right. Okay. So as you can see, the Pascal VOC challenge at the late years is a very challenging data set, and it is, as you say, they need well labeled data so that they can develop algorithm to attack the 4 tasks. Okay, so who is the organizer of the Pascal VOC? He is Mark Everingham. Okay, so this is his brief experience, and unfortunately, he is a good, I should say, contributor because he worked as an area chair in ECCV and CPR, even a program co-chair in BNVC, an editor at PAMI. Okay, PAMI is the, I should say, top journal in computer vision. But however, unfortunately, he died very early. So he died in 2012. Okay, that's also, okay, as you can see, the VOC Pascal VOC challenge also ended at 2012. Okay, there are for 2 reasons. First is, okay, he died. He is a main organizer, and now they lost the organizer. And the second is the emerge of ImageNet. So let's see. Okay, and to memorize him, now there is a PAMI Mark Everingham Prize Awards for significant contributors in computer vision every year. And we will see who wins the prize this year. Okay. So this is another famous data set called CFAR10. So who is the compiler? It's Hinton. So so I should say, who is Hinton? Okay, he is the winner of the Turing Award in 2018. He's a very, very, I should say, influence researchers, and he is not a, his primary research topic is neural network rather than computer vision. But however, as we will see in the following slides, neural network is a very powerful tool for computer vision, and many state-of-the-art computer vision algorithms all based on neural network. So, in 2009, he developed a very neat data set for neural network, also for computer vision. So why I say it is very neat? Because it has a very uniform resolution. All images are 32 by 32 pixels. And only 10 classes, just like the MIST. And there are 7 TK images in total, something like MIST. How do they get those images? there is another dataset called 80 million tiny image dataset. So they just use the existing dataset and crop 10 classes from the dataset to form the CIFAR-10. And there is another extension. This means CIFAR-100. The only difference is there are only 10 classes in CIFAR-10, and so there are 100 classes in CIFAR-100. Okay, in addition to those datasets, so of course, everybody can propose their dataset for some reasons. So this is a fashion and mist. So mist was released in 1996, and then fashion and mist is 2017. So the gap between the two datasets is 19 years. Why do they? So let's see. How many training images? 60K, almost the same as mist. How many? 60K training, 10K test, almost the same as mist. Pixel resolution, the same, and why do they want to propose the fashion mist? Because they think mist is too easy, mist is too overused, and mist cannot represent modern computer vision tasks. So they propose. So who proposed the mist? It is from Zalando. It's a company. What's the company? It's an European online clothing retailer. So everybody can propose their dataset for image classification task. And this is relatively new, MED and MIST. The first version was released in 3 years ago. 3 years ago. And the second version is last year, and the latest version is this year. So what is MIST? You can see from here. Let's enlarge them. So there are totally 18 data sets. Some of them are 2-dimensional, and some of them are 3-dimensional. So you can see that there are, you see the keyword 3D, it means a 3-dimensional data set. And because this is a collection of 18 data sets, so the number of classes in each dataset vary from 2 to 14, and the number of images also varies from 0.7K to 200, more than 200K. So it's just highly varies. Okay, so what is the uniform point? It's a resolution. Okay, 228 by 28, like and mist. So it's called MED and mist. So what's the difference from the version 1 to version 2? Version 2 has more images. And what is the MIST plus? The plus means they offer not only the small image, but also larger images. It can be 64 by 64, 128 by 128, 256, etc. Alright, okay, so now let's talk about the benchmark ImageNet. The dataset was originally proposed in CPR 09, and in the beginning, they planned to compile a dataset consisting of 4 million images, but now there are 14 million images already. And the number of classes is 21K. So why is the number? Why they choose this number? Okay, because let's talk about the idea of ImageNet. So who is the my contributor is Fei Li. Now she is a professor at Stanford University, and when she compiled the ImageNet data, she was a professor at Princeton. There was a existing dataset called WordNet. It is not an image dataset. It is a word dataset. Do you heard about this WordNet from your from Professor Gu? Okay, that's the idea. When artificial intelligence was developed around 20 years ago. Some linguistics, they want to, can we collect all words used by human beings? Yes, they can, because we have newspapers, we have books. If they want, they can collect it, because we have dictionaries, right? They can. So they compile a huge data set called WordNet. But it's not so far. It's not just a dictionary, because the dictionary only show, okay, what's the meaning of the word and how to use the word. They want to create another relationship. What is the relationship from one word to another word? So they call it a word net. Once they have those words, and once they can connect one word to another word, they will become a net, right? Okay, so those natural language researchers, they try to create the word. They try to explore some properties within the data set. Okay, so, but however, I am not an expert in this field, so I cannot tell more about what is their achievement. Maybe you can ask Professor Gu or Professor Jen. They are experts in this field. So, however, let's come back. So, Professor Fei Li got the idea. Since we have the WordNet dataset already, can we visualize that? Okay, so because some word is unable to visualize, but some word, in particular noun, is easy to visualize. Okay. So from the WordNet, there are more than 80K nouns, but some of them are synonyms. So they filter out all of those synonyms to get the remaining 21K nouns. So that is the reason there are 21K classes in the ImageNet. So once they have those 21K nouns, they use search engine. So in 2009, Google or some other search engines are very well developed. So they can collect a lot of images from the internet. But however, they don't own the copyright of those images. So they only collect the URLs of those images. Then their next step is to label them. Although search engines can provide those images, they still need human labels to label those images. And they found it is very difficult to label those images. The scale is too large. So they use label human crowdsourcing. It means if they pay American mechanical Turkers to label those images, and pay another group of American mechanical Turkers to check whether those images are correct or incorrect, so that they can create the dataset. In every class, there are at least 500 to 1,000 clear high-resolution images. So this is it suddenly became a very, very attractive and challenging classification task. Okay, but there are still too many, 21K too many. So they hold a challenge. This means ILS VRC, ImageNet. Okay, so the source of the images from ImageNet. Large scale, because as you can see, until 2009, the Pascal VLC is I should say top challenge, and there are only 20 classes. Now if they suddenly increases to 1,000 times, it's too difficult for everybody. So they only increase to 1K classes. Right? Okay. And there are only 1.4 million images, including training images 1.2 million, and the validation and test set 0.1. So you can see this image, this figure on our textbook. This is our figure 6.4. It is a comparison. Okay, it is show how and why the ISL VRC is a very challenging data set, because you can in the data set you can see very different images. Object scales means candle is very small, right? And oyster relatively larger, cannon, and spider web. Okay, so how many instances is an image? It's only one, but if they're stacking, there are two. Mushroom, there are 1, 2, 3, 4, 5, and strawberry, there are a lot of strawberries in a single image. So that's the reason why. So you can see there are other factors. Image clutter means campus, very simple, just one campus at the center of the image, and still drawn. So we can recognize this is still drawn, but how to recognize from a single object? No. If we want to, so this is a still drawn, a small part of the image, okay, and the deformability means if it is a canoe, yes, it's a single solid object. But if it's a monkey, okay, the monkey will have many different poses and I should say location, etc. So that's the reason why ImageNet is a very, very challenging data set. Okay, let's compare. So our I should say Slutsky also very kindly show us what's the difference between Pascal VOC dataset and the ImageNet dataset. So because there are only 20 classes in the Pascal dataset, so there is a class named bird in Pascal. But in ImageNet, there are a lot of different types of bird. Flamingo, cook, I don't know how to say the sun, goose, etc. Okay. The same cat. There are only single class cat in the Pascal VOC dataset, but there are Egyptian cat, Persian cat, Simon's cat, even lynx in dataset. So as you can see, one class in a Pascal dataset can be separated into many different subclasses in the image dataset. So even in the image dataset, their labels are not a single label. There is a hierarchy label from layer 1 to layer 9 because there are 21K classes. Okay, so now we have a very, very challenging data set, ImageNet, or we say the ISL VRC if we want to clearly specify it. Okay, so for the ISL VRC data set, this is the best, the winner of the challenge year by year. So from the beginning, because the ImageNet was compiled and released in 2009, so they host the challenge from 2010 to 2017. So as you can see, year by year, researchers developed better classification algorithms to attack the challenge, and year by year, they generate better and better results. So this is the human performance. This means given so many images, ask a human, okay, well, which class do you think those images belong to? Okay, then the average of human beings, the error rate is around 5.1%. But if they use computer, they use algorithm, year by year, and in 2015, human performers become worse than computer. So now let me see, there is a label. It's shallow and 8 layer, 19, 22, 150. So what's that? That is, if it means shallow, it means it is not used deep learning. And when they started to use deep learning, one key factor is the depth of the network. So in the beginning of the deep learning for the image classification, there are only 8 layers. And then it increased to 19, 22, and increased to 150. The deeper the network, the better the performance. It also shows the improvement of neural network is along with the improvement of image classification accuracy. So that's the reason why Hinton's contribution is very significant, because he founded many important algorithms for neural network, and then those algorithms and the method boost the performance of image classification. Okay, now let's take a look at first. What are the shallow algorithms? Because you will get a sense. Oh, so let's go back to the feature-based method. So in our textbook, our author Zaleski mentioned a bag of words algorithm. It's easy to understand. So the bag of word algorithm first was used for document classification. It means given two documents, how do you know they belong to the same class or not? If you have a lot of sample training documents, and the straightforward idea is, okay, since there are many words in a document, can I collect all of those words and let's do not consider their order, we just collect of that. Then we can use some vector to describe the document, and then we can compare those feature by feature against another document. So we can see, okay, if this vector is closer to something, then maybe, okay, this belongs to the same class. So they developed, there is a method called bag of visual word. Only difference is one is the text word and another is visual word. So what it means, given an object, if I can extract some key points from the object and treat them as a bag of words, then given an image or given a few objects, I extract those key points or components. Then I can create a vector. Then I can compare those vectors to classify which image, which class the image or the objects belongs to. Okay. So, but however, given an image, okay, so let's go back to the problem again. So let's see this. For the Xerox 10 dataset, their resolutions are different. So how do you crop those patches from the image? Because they are different scale, how can you fairly extract that? It's very difficult. So they propose to use gradient rather than patches to form the word, to present the word. Okay. So their idea is, given an image, so if you just focused on those key patches. You don't need to care about the resolution of the image. They first identify some key points from the test image, then extract features from those key patches or key points. Then they use those features, no matter the number of features. They can create a histogram, then use the histogram as the feature to present the image. Finally, they can apply some machine learning algorithm. So for example, support vector recognition or data boost to create a classifier to classify which this image belong to certain classes. Okay, so the first is how to select the key points. So there are three different. Roughly, we can categorize every pixel into three classes. One is corner, another is edge, and another is a smooth region. Of course, key point should be corner, or at least edge. The reason is corners are relatively rare in an image. And if we can find one corner and find another corner, then however we can, if there are some shift between the image, okay, they are still rare, so that we are easy to match them. But however, if there is an edge, then there are usually many pixels have the same shape along the edge. So even worse, on a smooth region, there are many similar pixels in the smooth region. Okay. So let's see an example. From the left image and the right picture, they are highly similar. They are just taken from a different shift of the orientation. So this is edge. If you localize this patches here, and you want to find another pages in the right image, very unique. Okay, you can find it here. But if you find an edge patch here, this looks like this. Then yes, you can find another highly similar patches look like this. But however, are they located at the same position? No, in fact, there is a shift, because you can see the ideal for here. Okay, let me wait. Okay, as you can see, because this we can identify here, so it is just along here. So ideally from here, okay, the correct patch should be somewhere like this. So there is a significant shift. Furthermore, if we use a smooth patch, then okay, you can find from here, you can find a lot of similar patches in the smooth region. So so this becomes a problem. How do you find edge? Sorry, how do you find corner? There is a very famous feature called shift. Shift in the algorithm law. This is the algorithm proposed by law. Law use difference of Gaussian to find the edge pixel. So what is the difference of Gaussian? So take a look. This is the high resolution image. Then if we apply a Gaussian filter and then we control the kernel width, you can see this is slightly blurred, and this is further blurred, and this is further blurred. So this is a high resolution image. If they reduce resolution to a smaller scale, this one, and even apply the Gaussian filter, so you can from this you can see a slightly blurred, and more blurred. So there are two factors. One is the resolution, from large to small. One is the clearness, from very clear to relatively blur. So it call it a octave. Then when they have those octaves, they subtract one layer from another layer. They will get the difference of Gaussians. Then they find what is the minima, local minima. It is even a local maximum or a local minimum. However, they want to find the extras. So they compare pixel by pixel. It means given a pixel, it can because there are several layers. Right? Though they compare, there is nearby 26 neighbors. If they can localize, okay, this is the extrema, then it is highly possible it will be a corner. So this is just the first step. They search all of the possible pixels and find some candidates. But however, they will still need to check whether its gradient is large. If its gradient is not large or there are some similar gradients nearby, it means it may be an edge rather than a corner pixel. But however, use this method, they can find many corner pixel, and this is the key point. However, this is the first step. Once they find the corner step, okay, they will use the gradients nearby those corners to create a histogram of gradient. So it means this is just an illustration. Suppose that at the center is the corner pixel. Then there are 4 pixels, and at the left top region, every pixel will have a gradient. So what does the gradient mean? There are 2 factors. One is the magnitude, how large the gradient is. Another is the orientation, from 0 to 306 degrees. From these 16 pixels, okay, if they divided the orientation into 8 bins, it means 0 to 45, 45 to 90, 90 to 135, and collect gradients belong to the bin, sum those magnitude up. Okay, so if they use this region, and then this is a collection of those gradients, the collection can be converted into a histogram. Then, given a pixel and some nearby regions, they can create several histograms. So this is just an illustration, and as you can see, this image is also available in our textbook. But in fact, shift, so this is just an illustration. And in the real shift feature, they not use, I should say, their region is slightly larger. So suppose this is a corner pixel, and then they will use the 16 by 16 pixel region. And for each region, they will create a 4 by 4 subregion. And from the 4 by 4 subregion, they will get the histogram. And the length of the histogram is 8. So totally, they will create a feature vector. The length of the feature vector was 18. Why is it? Because there are 18 subregions. And within every subregion, there are 8 bins. So the length will be 128. That is the real shift feature. And in addition, okay, because we want to describe the edge, so as you can see, the pixels far from the center will be less important. Therefore, how to control the factor? Easy. They apply a Gaussian weight to reduce the weight or the influence of the pixels far away from the center. So they will focus on something closer to the center. Okay, so this is the complete shift feature. Once they Okay, I should say, let's go back here. Okay, now they can detect many edge or key points, and then they can extract features. It means the 128 dimensional vectors. Then, as you can see, there will be a lot of key points. And so how from the whole data set, let's see, go back here. Okay, as you can see, there are totally 3,000 images. From those 3,000 images, every image you can extract several hundred or even several thousand edges. And from those edges, you will create a very large number of shift vectors. So what's the next step? The next step is they will use k-means. So k-means is a clustering algorithm. It means given a lot of suppose the every pixel is a point in the 128 dimensional space. Then k-means can cluster those feature vectors into some groups. So this is an example. If they cluster those points into 10 groups, it will look like this. It will something like segment the feature spaces into k subspaces. However, so this here k is a hyperparameter, and they extract 10k shifter feature, 10,000 shifter features into k cluster. So why do they need to do it? Because they want to define some anchor point in a high dimensional space so that they can describe an image using those anchors. Okay, let's explain it again. Okay. Here. Now we don't know how many features will extract from a single image. But however, if we have some predefined anchors in the 128 dimensional space, then we can convert those features into a histogram using those k cluster centers. So that's their purpose. Therefore, they can describe an image rather than just describing those key points. Okay, so after the clustering, once they have a test image, they extract those shifter feature and find the closest cluster center so that they can create the image descriptor. Then they just apply some method, machine learning method to classify those images. Okay, so let's take a break. Okay, do you have any questions? No? Okay, let's go on. So they tried two different classifiers. One is multi-class supported vector machine, and another is AdaBoost. So multi-class supported vector machine is relatively simple because it's okay. Just do you mean supported vector machine? Yeah, okay, good. It's good. So it's very, and so therefore the key point. Okay, the hyperparameter is the k. Because they finally convert an image into a k-dimensional vector. So if the k is larger, it means there are more clusters in the dimensional space as their anchor. Then, of course, since there are more anchors, then there will be more. The vector length will become longer, and more information will be preserved in those vectors. So their accuracy is relatively better. But however, you can see the error rate almost converged around 26 percentage. It cannot further reduce the error rate. So here, as you can see, the 26. Let's go back to the performance of this chart. Okay, you see. So 26 is very similar to the 28 or 25. So that's the limit of the back of word algorithm. Okay. And to visualize, okay, as we mentioned, this is a multi-class supported vector machines limit, and they also try ADA boost. ADA boost, what is ADA boost? ADA boost is another type of classifier, and the main idea of ADA boost is if there are many weak classifiers, and they try to find a way to combine those weak classifiers into a single strong classifier. So how to do it? Tune the weight or coefficient for each classifier and combine them together. So let's see an example. If suppose there are only two classes in this image, the blue orange triangle and the blue circle. So they can find a very simple classifier. Just use the x2 as a threshold. If the value of, because for each, suppose this is, I should say, suppose their vector is just their coordinate. So there are only x1 and x2, two feature elements. So for every blue, so they find the first simple weak classifiers. We use x2 as a threshold. If the value is greater than a threshold, then I think the weak classifier treat them as the blue class. Otherwise, treat them as the triangle class. So of course, because it's a weak classifier, it makes some mistakes. So these two picked points are misclassified. Also, therefore, ADA boost will increase the weight of those training centers. So now it becomes more important. And they find the second weak classifier. In this case, they try to use x1. So this is a second weak classifier. If the value of those points is x1 is greater than the threshold, it will think, okay, it is the triangle classes. Otherwise, it is the circle classes. Okay. As a result, okay, the two training points are correctly classified, but the three training points are misclassified. So they increase the weight of the three training examples. So you can see the circles become larger. Okay. And therefore, they created a third weak classifier. This time, they will use this. Another threshold on the x1 axis. Here, okay, so they can combine the first weak classifier and the second weak classifier and the third weak classifier to create a strong classifier. It looks like one. This, and this. Okay, I should write that. Okay, so decision boundary of the combination of the three weak classifiers will become this. So it can better classify the two classes. So this is the idea of ADA boost. Okay, so here, let's go back to the, okay, now let's go back to the process. First, they can extract a lot of key points. Then they will present those key points using shift feature. Okay, here, it will be an issue. How do you define the weak classifier from this descriptor? So they try a lot of different classifiers. For example, they can use, because we have a lot of we have K cluster centers in the 100 in the shifted space. So for chair, for the chair classes, they will ask, so what is the major cluster centers the chair classes the features will belong to? So they labels and they show us 3 major cluster centers. It is the red, yellow, and the green circle. So what does it mean? As we can see, this is if we get a shift feature, it is the descriptor for orientation and for scale. So they use the shape of the circle to describe the shift, actually to present the shift feature. So for class, so okay, if there are some vertical edges and the scale of the horizontal edges and the scale of the edges is not very small, just belong to a certain scale, then it is likely it is a chair. And for the road sign, they found the most useful weak classifier is if they are 2 clusters with similar scales. So it means the blue circle, they belong to 1 cluster, and the green circles, they belong to another cluster, and their scales are highly similar. It is an effective weak classifier to find or to recognize the road sign classes. And for the bike classes, they found that the most useful weak classifier is if there are 2 shift features, one is smaller and one is larger. The one shift feature will cover another shift feature. It looks like what? Because if there is a bike, there are tires. If there are tires, it means they are usually very strong contrast along the tire. So the small shift feature will be covered by a larger shift feature. And for boat class, they found the most effective weak classifier is there are many small shift features and they overlap with each other. So what does it mean? It is mean if there is a boat, usually there is some very clear vertical edges, and the vertical edge, the width of the edge is not very large, okay, big. But however, it is often found in the boat images. Okay, so that is the approach they used to classify image without neural network. They used the bag-of-word method. So let's think about what's the limitation of bag-of-word. The bag-of-word is, so this is bag-of-word. Can it from this image? Yes, it can. And it can enter from this image? Yes. So the limitation of bag-of-word, it doesn't preserve the structure of the source image. So that's the reason, because it has a limitation. So as you can see from here, when they apply the bag-of-word method, the error rate, no matter how they develop the algorithm, it cannot be lower than 25%. Okay. So let's go back our textbook. In our textbook, there is a section describing the path-based model. So what is path-based? Okay, it means given an image, okay, if you can recognize part of the image, then you can help you to classify the overall image. Okay. And the idea has been developed for many years. So this is an example. What it looks like? It looks like human faces. So on a human faces, there are several facial components. There are 2 eyes, a nose, a mouth, and 2 ears. Also, there's a hair. So if you can model their relation, their distance, okay, you can recognize whether this is human faces. Then you can classify where this is the image of human faces. And there is a example. It's called 5-gram class. So see, all of them are images of birds, and each of them is a species. So the 3 images A in the column A are the same type of breed of bird. The image of column B, the same, is a breed of bird. They are 2 different types of bird, but visually they share the same color, but similarly the same shape. So how to classify one breed of bird from another breed of bird? So this is a 5-gram classification problem, because the significant difference is the textures on the head and the textures on the breast. The same for the column C and the column D. They are 2 different types of birds, but it looks very similar to each other. So there is an algorithm proposed in ECCV 14. They use part-based method to deal with the 5-gram image classification problem. So what does it mean? There are many types of birds. If they can localize the whole body in addition to the head, in addition to only the body part, then they can increase the chance to correctly classify the type of the bird. So in 2014, the state-of-the-art object recognition detection algorithm is RCNN. It means Regional Convolutional Neural Network. So it can create many proposals. It means the possible region of an object. Therefore, they can, from this image, they create many proposals for head. So this is the possible of the head, but there's another possible. If they can correctly find the head from the image and the whole body and only the body part, they will create a result like this. So the first question is how to correctly recognize, this is a part of a bird. Their approach is very simple. They have a pile of training images. So this is their training images. And in the training images, they have labels. Where is the head of the bird? Where is the body? And where is the totally overall image? Once they have the proposals, they compare the test image with every image in the dataset to find the most similar one, and use the labeled information to pick up the best candidates. So how do they measure it? Because RCN is a network, there is layer by layer. So they extract the pool 5 feature vector from the RCN, and then because it's a vector, so from those training examples, they have extracted those features already. So they just need to find the most similar vector in terms of cosine distance. So therefore, the definition for cosine similarity is given two vectors. If their vector length is the same, it means the inner product of the two vectors divided by the length of each vector. So it will become a value between -1 to +1. If they are +1, means the two vectors are identical. If the value is 0, it means the inner product is 0. It usually means, if we describe it in a geometric, it means the two vectors are perpendicular to each other. Okay. As a result, given the image, they can search their data set of find the similar images. For this example, they find that the most 5 nearest neighbor are the 1, 2, 3, 4, 5. Okay, so as you can see, from here they can use the information. Okay, this is the head of the bird, and this is the body of the. As you can see, there's the location of the head and the location of the body are similar to each other. Given this example, you can see, okay, the location is almost at the left top corner of the image, and the body is at the center. This one is the set. The head is at the right top corner, and the body is around the bottom center. Okay. As a result, but however, okay, they compare their method with some existing method. So this is the ECCV12. This is a deformable part model, and they use RCNN. So the strength of the neural network can be shown here. If the neural network is very effective, it means you can find better feature to describe the image. The deformable part, okay, it doesn't use neural network. It just try to find some part which can move somewhere or change its shapes. But however, their algorithm not always works. There are some failure cases. For example, if you see this image, what does it mean? The algorithm predict this region is the head of the bird. Of course, it makes a mistake. The head of bird should be here rather than here. And what's the problem of this image? Of course, the rectangle should be somewhere there. It should be a bounding box for the body, but something wrong. It includes too much background. All right, but however, what we see here is, if you want to classify an image, there are many approaches. They combine neural network along with body part model. So it is very useful for the fine-grained image classification problem. Okay, in general, when we classify an image, we use content and the scene. And this is the example image shown in our textbook. The question is, what is this? When you see the image, okay, and if you this is a interesting psychology problem. What is this? Is it a bottle? And what is this? Do you think it is a cell phone? All right. And what is this? A person. And what is this? A car. And what is a shoe? Okay, so the answer is they are all the same. They are manually created. The appearance are totally the same. So how do we judge whether this is a phone or this is a button? We not use only pixels on the region. We use information of the context Because you will see, okay, there's something on the top of the desk. It should not be a person, right? Because if you pay attention to this region and region, they are totally the same. So this is also another issue for image classification. Okay, now we see the data sets. We see some shallow, so this part method, this is a back of word, is a representation one. Now let's go to the neural network based algorithm. So here first, as you can see, the error rate dropped from 25 to 16. It's a huge improvement. And how do they do it? Okay, so there's a summary. Okay, in 2012, AlexNet. Okay, this is the first deep network to address the ILS VRC challenge. And then the next year, there's a very, very similar network for FS network. Okay. It further improve the error rate. Okay. And then 2 years later, VGGNet was proposed. It increased the depth of the network. And in the same year, GoogleNet is also proposed. But they use very, very different architecture. Then in 2015, ResNet was proposed. It hugely increased the depth of the network. And then in 2016, ResNext, okay, it is a combination of GoogleNet's inception module into ResNet. And so if next, they didn't show the, okay. The DenseNet it was also proposed in 2016. We will see DenseNet later because in the third class of this course, I want to deeply discuss a paper. Using DenseNet for X-ray classification. Okay. And in 1917, SENet here. Okay. This is the winner of the last year of the ISL VC challenge. Okay, so let's go. So if we want to talk about the AlexNet, we had better know what is LaNet file. LaNet was proposed by Yang LaQuan. So this is Yang LaQuan, and he and Hinton, Geoffrey Hinton, and Yosha Benjo. They shared the Turing Award in 2018, okay, because of their contribution for neural network. And Yang LaQuan's contributions, he developed the LaNet, and this is the first, I should say, he proved convolutional neural network can be very useful for recognize image. But however, in 1918, he recognized the M-MIST dataset. So as this is architecture. Given an input image 32 by 32, and as you can see, this is 32 by 32. But you may ask the question, why was we mentioned the resolution of our M-MIST is 28 by 25? Is this different? Okay. The reason is, in the network, when he uses convolution, it will create a boundary. So he needs to extend the image a few pixels wider, so that when he apply the convolution operation, he can reduce the missing boundary. So this is the input image. Then it will apply a convolution. The kernel size is 5 by 5. Then it will generate the first layer. A layer means a set of channels. Each channel is a feature map. Then there is a subsampling. Young LaQuinn used the average pooling, but now many people use maximum pooling. Pooling means given for say 2 by 2 original 2 by 2 pixels. They only so average pooling means compute the average of the 4 pixels, and the maximum pooling means just take the maximum value from the 4 pixels. Okay, it will become a new set of feature maps. Then apply a convolution kernel again, and it will generate the second layer and do subsampling. This means apply a pooling. Okay, then this is a third layer, fourth layer, and the fifth layer. So from the fifth layer, there are 10 outputs. So how do they, from the 10 output, they can use the value of the 10 output to predict which this image class is. Therefore, because there are only 5 layers, 1, 2, 3, 4, 5, the network has a name, the net 5. The 5 means there are only 5 layers. And okay, so this is the net developed in 1996. And in 2012, it means there is a gap of 16 years. And in 2012, the Internet challenge is already there. And why it is called AlexNet? Because this paper is they released a paper, and the first author of the paper is Alexandra, so it is called AlexNet. And who is Alexandra? Alexandra is Hinton's student. So as you can see, Hinton, he is an expert in neural network, so he knows this architecture very well. He just asked his student use a neural network and apply it to the ImageNet challenge. So in the AlexNet, the architecture is all totally the same as LaNet. That is why. Okay, see, this is the input image. Okay, the resolution is 217 by 217 by 3 channel. Here, this is single channel because MIST is a grayscale image data set. But ImageNet challenge, all of them are color images, so they are 3 channel. Apply a convolutional kernel and get the first layer, and apply the maximum pooling. Okay. Then apply the second convolutional kernel and the maximum pooling. So get the second layer, and the convolution, the third layer, the fourth layer, 5th, 7th, and 8th. So there are totally 8 layers. And as you can see, so the last 3 layers are what? This is a fully connected, also called multi-layer perceptron. So it's totally the same as the last 3 layers, multi-layer perceptron. And their first 5 layers is what? Convolution, so subsampling. So that's all. So they just added more layers in the beginning. Why? Because the image resolution in the LaNet is only 32 by 32, but for ImageNet it is 27 by 200. Since the resolution is larger, they need more layers, and so that they can downsample the resolution to adequate size to convert into the fully connected layer. And however, the result is very impressive. So that's the reason they significantly reduce the error rate. But however, there's another question. If this is so useful, why there is a gap of 16 years from LaNet to AlexNet? The reason is the first, data. Before ImageNet, they don't have sufficient data to train a neural network. Because in a neural network, there are a lot of parameters you need to tune. And the second reason is the computational resources. In 2014, now you see this is the AlexNet. Okay, but let me think. How, in fact, they separate the network into two networks. The reason is why. Because in 2012, the best GPU they can get is RTX 580. And the VRAM of that GPU is only 2 giga. Not enough. They need 2.8 giga to store all of these parameters. So then at the end they need to separate the single network into two networks. But however, the architecture is the same. Okay. And then the ZFnet, the winner of the challenge in 2013. Okay. So this is the upper part is the figure of the paper of ZFnet. But if I found an interesting figure like this one. It converts the figure in the format of the AlexNet. So let's make a comparison. What is the difference between ZFnet and AlexNet? So you can see the lattice 3 dense layers are totally the same. Dense. And the resolution of the 8th, 7th, and 8th, 4th, and 3rd layer are totally the same. You see the number 113, 348, 13, 348, totally the same. So what's the only difference? The only difference here, for the first input layer, they use a 7x7 kernel vector. And in the XNet, they use a 11x11 pixel kernel vector. So this is a smaller kernel vector. And also they adjust the stride number. Stride means for convolution to kernel. And the next convolution, how many pixels will be the shift. And in the AlexNet, the stride is 4 because their kernel size is 11x11. So they choose 11 and skip 3 pixels and go to the next 11 to 11. And here they just adjust the two hyperparameters and they further reduce the error rate 5%. This means a lot. Okay. So what does it mean? It means there are a lot of, I should say, settings you can tune so that you can improve the performance because there are too many parameters in the network. So there are a lot of different ways those researchers can try to fine-tune the architecture. Okay, then the VGGNet comes. So let's take a look at the VGGNet. What is its specialty? First, it is relatively deeper. There are several different configurations. The VGGNet, it can be 11 layers or 13, 14, or the deepest is 19 layers. And they use very, very simple structure. It means all convolution kernels are 3x3. Okay. So they compare, okay, so how many parameters are in their network? So in the configure A, there are 133, and configure E, there are 100. So if they change the configuration, they will also change the number of parameters. And let's see the GoogleNet. GoogleNet, the idea is they want to develop a very efficient network. So how do they do? They propose this is the inception module. From one layer to another layer, they use many one-by-one convolution. So what is one-by-one convolution? Let's take a look to a figure first. One-by-one convolution means this. So this is a layer. There are height, width, and many channels. One-by-one convolution means they use one. So one-by-one means if they convolute the channel, the layer with one-by-one, they will learn a set of parameters in the kernel, and it will be sum those channels up into a single channel. Okay, so this is one-by-one. So what does it mean? It means you only need, in this example, you only use 192 parameters, but you can increase the nonlinearity in a layer. So that's the meaning of it. So you don't need to spend too much, just a few parameters. Then, okay, you can create the nonlinearity of the network. And why nonlinearity is very important? Because neural network here, they worked as a function. So let's go back to the okay. No matter for LANet or for AlexNet, what is input? It is image with what? Fixed resolution, fixed dimension. So what do the two networks works like? They works like a function. Given a very high dimensional vector, they will convert the vector into 10 digits or 11 digits. Okay, and from those digits, they will use the value of digit to predict the classes. So if you can create the nonlinearity in a network, your function usually will work better. So that's the idea of GoogleNet. So they use many one-by-one convolution here, so that they won't use a lot of parameters. They can still create good nonlinearity. And here is let's compare. Okay, so this is the size of GoogleNet. They are relatively smaller, and this is a VGG. So the radius of the circle means how many parameters they use. So here we can see from the table, VGG 16 is the configuration D. So it uses 138 million parameters. It is this case. So 138 parameters. So however, GoogleNet, is very small. It's around, I think, 10 million parameters. So this is the advantage of GoogleNet. And this is their performance. GoogleNet is here. Okay, its accuracy is around 70 plus, 60 plus. Okay. Okay. So I need to clarify here. Here you see is the top one accuracy, right? Okay. So you see the GoogleNet, I think is here. Okay, is around not less than 70. But if you see this chart, okay, you will see the achievement of GoogleNet is around 60.7. Why they are different? Because if you see this is the 6.7, it means its accuracy is around 93 percentage. Why? Because this is another measure. This is a top 5 error rate, and that is a top 1 error rate. It means, okay, so it means, see, there are 1,000 classes, right, in the ImageNet, and you will generate the prediction of the 1,000 classes, each one. So there, the final layer is an array of 1,000 values. So top 1 means your highest value should be the classes. Otherwise, you will the result will be treated as misclassified. But top 5 means if the top 5 number, one of the top 5 numbers is the ground truth class, then it means your judgment will be treated as correct. So top 1 is more difficulty than top 5. Okay. Alright, so this is Google and the ResNet, the winner of 2015. So the improvement of the ResNet is they found if they just pass the signal. So let's go back here. So when you do convolution, you pass the signal, and do convolution next time, you pass the signal layer by layer. But if there are too many layers, your signal, it will, in the beginning, it may be very large, but in the end, it will become very, very small. And it is very difficult if the gradient is very small, it will be very difficult for you to update those parameters. So the key point of ResNet is they not compute the signal. They compute the residue of the signal. So you can see there's a bypass. And this is the bypass from layer to layer, from layer to layer. It means when you have an image, they focused on the residue from the image to image, and finally they will get the same 1,000 numbers. Because they focused on residue, so that even though the number of layers gradually increased, the gradient can be passed through those layers. Okay. Well, and finally, this is the winner of the last year SE net. So what is the SE net? It means squeeze and excitation. So what is squeeze excitation? This is just an idea. It means this is a layer, and they can add more parameters to learn the relationship between those channels. So suppose there are C channels. They use more parameters. It will the squeeze means to average pooling to create a average of every layer. So it becomes a 1 by 1 by C vector, and use their parameters to adjust the weight of each layer and then so times those vectors back, so they can adjust the weight layer by layer. So this is the way to adjust the parameter. So however, the problem is they need more parameters. So how many more parameters they need? Okay, let me show you a comparison. Okay, here, yeah. So this, as you can see, ResNet 152, it requires around 6 million parameters. But how many parameters needed in SCNet? It requires around 150 parameters. So it is about 2.5 times of the ResNet 150 times. Because of the extra parameters, they can boost the accuracy from around 77 to 82. Okay. So what is SCNet? It means use more parameters to adjust the weights layer by layer, so they to generate better performance. So let's see what is the S and E squeeze and excitation block can be inserted to any type of networks. So this is their example to insert the SE block into the GoogleNet. And this is the example. They insert the SE block into the ResNet. So take a look of a step here. So global pooling, what does it mean? It means so there are many channels. We say we mean average pooling and maximum pooling. Global pooling is a type of average pooling used. So average pooling usually just applied for a region. That's 2 by 2, 3 by 3. Average pooling means the whole map of. Okay. So because they are C channel, apply the average pooling for the C channel, we will get the result of C value. So this is the C value, and there is a fully connected layer. So that is the extra parameters, and do ReLU, and do fully connected layer again. Because of the ReLU, they increase the nonlinearity. Okay, and then they apply the sigmoid activation function. Sigmoid expansion also increase the nonlinearity, but less than the ReLU. So with the more parameter, they are two fully connected, and the two activation function, they increase the nonlinearity. And then this is the new coefficient. They apply coefficient to the scale to get the new layer like this one. Alright, then after the SCNet, there's no more ImageNet challenge. So, but there are still more methods developed to attack the task. So this is the EfficientNet. It is developed by Google. What is EfficientNet? The idea is very simple. We say there are many parameters for a neural network. Its width, its depth, and the number, the used resolution. So the idea is, if there are so many hyperparameters we can set, how about let the computer to search what is the best combination of those hyperparameters? So that is they use NAS, Network Architecture Search, to do it. Okay. And so they generate a very good results. So let's take a break now. Alright, so as we see, the EfficientNet is a result of NAS, Network Architecture Search. So there should be some basic architecture so that they can apply the NAS to search the best hyperparameter. So what is the basic architecture? It is mobile net invert bottleneck and the SENet squeeze and excited block. So what is mobile net? Mobile net is another network developed by Google too. The idea of mobile net is very different from the VGNet. So let's see this chart again. There are a lot of huge network, but if a network is very huge, can it run on a mobile device? Because they are very limited memory size and computational resources on mobile devices. No, it's impossible. So the purpose of MobileNet is they want to develop a very small, tiny dataset, easy to run. They can sacrifice the accuracy. This is fine. So that's the purpose of MobileNet. In the beginning, there's a MobileNet version 1, and there's MobileNet version 2, and MobileNet version 3 and 4. This year, MobileNet version 4 was released in ECCV this year. Okay, and the MobileNet 2 from the is an improvement, and MobileNet 3 it used some special operation so that it is not popular. Okay, only limited devices can use it. But here, this year, MobileNet V4 can be run on almost every kind of devices. In particular, because our mobile device cell phone is also improved year by year, and the GPUs in cell devices become there are more resources available there. So MobileNet V4 is one of its features. You can use a variety type of GPUs on mobile devices. Okay, this is the mobile version. I should say EfficientNet V1. It was published in ICNL 19, and 2 years later in ICNL 21, the same team from Google, they released the EfficientNet V2. So this is a comparison from EfficientNet V1 and the EfficientNet V2. You can see the measures in addition to its improved accuracy, they significantly reduce the training time. So why? Because they still use NAS, but they replace the block called MB-convolute in EfficientNet with a new block called Fuse MB-convolute. And the Fuse MB-convolute can better use GPU and TPU. But however, there's a problem. They cannot replace all MB-convolute with Fuse MB-convolute. They need to find the spot point. What is the best ratio of the fused MB-convolute? So they use NAS, network architecture search again. Okay, then this is almost at the end of the convolution because a new powerful tool appeared. That is the vision transformer. Because you have took Professor Gu's course, you know what is transformer, right? Now, so in the beginning, it was a tool for language processing. Okay, so and you know the attention mechanism, right? Okay, but what is vision? So the attention mechanism has been used for computer vision in NIPS 20, but it's not very successful because they cannot generate high performance, best performance. One of the problems is the computational load. So if they treat every pixel, okay, to use the as the token in the transformer architecture, then what is the problem? Say it is a 200. If there is an image of 200 and 214 pixels, why do we use the number? The number is because when we take an AlexNet, this is the first neural network architecture. They use 227 by 227 because the image. Let's go back to the table. Okay. Yeah, this is an image data set. The resolution of the image, because they grab the URL from the internet, so the image size are very different, from 4.2K to 12 and million, very huge. Therefore, but however, neural network, it works as a function. So you need a uniform input to to the function. So they downscale those images into 224 by 224, and they slightly expand the region. Okay. So we can see here it became 224 and 224. It almost become a standard for the state-of-the-art neural networks. Therefore, I use the number here to illustrate the difficulty of. If we have such an image, then what will be the number of pixels? I should say the number of tokens. There will be 50k tokens, and the depth of each token is 3 elements. The computational load for self-attention is n squared times d. It is very, very huge because now we have a very large number d here. And for convolution, the computational load is n times d squared times k squared. And the k is what? K is the kernel size. Because we use here, as you can see, what's the kernel size? 11 by 11, 5 by 5. It's relatively smaller than n. N is 50k. Okay, so this is the reason why self-attention, if they simply apply the self-attention to computer vision problem, it doesn't work very well. But however, in Lecture2, a very important method was proposed by Google. They first split an image into many patches. The patch size is around 16 by 16. So their paper's title is image is worth 16 by 16 words because they crop the image into patches. Once they have the patch, they use a linear projection. It's something like a convolution. So they convert the patches into a vector and then combine with the positional encoding. So they can create the token and use the transformer architecture to exploit its self-attention mechanism to do image visual tasks. All right. Once they develop a method, they compare the performance of a vision transformer and some state-of-the-art CGU-based algorithm. So this is the ImageNet. So there are only 1,000 classes. This is ImageNet 21K. 21K means what? So let's go back to the table again. It means we use all, so okay, ImageNet, there is a 21K classes. And the LOS VRC challenge only use the 1,000 classes. So ImageNet 21K means what? They use all classes, use all images. Okay, so it is a 1 million against the 14 million. So it means the data set become much larger. And even they use the ImageNet 21K, let's see the performance. This is the BIT. It means big transfer. Big transfer. It is a extension of ResNet, and it is state-of-the-art of this year. And there are several different configurations. So from the lowest configuration to the highest configuration, this is the range of the performance of big BIT. And the best vision transformer cannot perform better than BIT. But however, if they use an even larger data set called JFT300 million, so they are 14 million and they are 300 million. Okay, in this scale, vision transformer generate the best performance. And okay, yeah. So they also show this is the comparison across 3 different data sets. If they only use a single JFT data set and different number of training images, what will happen? They found when they increase the number of training images, the performance of the vision transformer improve. So what does it mean? Vision transformer is a method require a lot of huge images. If they can get those images, they will perform well. Otherwise, okay, they doesn't work very well. So as we see, the 2017 is the last year of the ISL VRC challenge. But however, there are many new methods they propose. So as you can see, in 1921, vision transformer is the best algorithm for the ImageNet challenge. And then you can see there are some more algorithm was proposed. They generate better performance. One of the reasons is they use extra data so that they can exploit not only the training images in ImageNet, but also others just like this, JFC 300. Once they use better other images resources, they generate better. So this is what is called OMI-VECT, and the arrays with VIT. It is a vision transformer based method, but they use more data. All right. Okay. So let's talk about. So since currently the state-of-the-art image classification methods are all VIT based rather than CNN based, but why we CNN based? So if so, then what is the problem of a CNN based method? Okay, the problem of the CNN based method is the inductive bias. It means when we use CNN, so what is the inductive bias? It means there is some explicit or implicit assumptions we can train our network, or we can train our model, or let our algorithm learn something from our data. And what is the inductive bias of a CNN network? This assumption is nearby pixels are more important than faraway pixels. Why? Because this is the AlexNet. When we use a convolution kernel, what does it mean? We want to know the relationship for a pixel to the surrounding pixel. So how large is the surrounding? 11 by 11. And so for a pixel here and a pixel here, when the information between the two pixels will be merged, it will be very late. When we use the fully connected, okay, their data will be overlapped. But the vision transformer doesn't work in this assumption. Let's take a look at the vision transformer. When we crop those patches, and so for this patch and for this patch, in the transformer architecture, will they information merged, will interact in the beginning? Yes, they will. Because of what? Because of the self-attention mechanism. They can look at each other in the first or even the further layers. Okay. So that's the reason, or that's the inductive bias. In fact, some researchers in very early, for example, in 2019, they found the problem already. That's the way they prove it. So this is skin of an elephant, and this is a object of a cat. If they combine the two images into this one, and they ask a CNN-based method, what class this image should belong to? Okay, the CNN-based method will say, "Oh, this is an elephant." Why? So our human being, we say this is a cat. But for CNN based, they think this the reason is texture. CNN, because we know CNN, they will look nearby pixel first. So in this case, if they only pay attention to nearby pixel, they will see, okay, this is the elephant because of texture. So CNN are good for texture but poor for age. So they further test the different cases. This is the original image, and they use AlexNet, GoogleNet, VGNet, and ResNet for human. All of them are correctly correct. If they convert it to grayscale, it is fine. But if we convert the image into silhouette, then okay, all CNN-based method performs very poor. And if we convert it into edges, well, very further poorer. Okay. So this is their evidence. Okay, so now because vision transformer has become the, I should say, primary leading, or say the most important image classifier method. So in very new paper, you will find they prefer vision transformer first rather than CNN, and they will show some comparison. So this is a paper for Dino. Okay. Dino is the it is a self-supervised model. Okay, so they compare their Dino under different architecture. This is a vision transformer for different setting. 16 means the patch size. The S means the number of layers, and also compare with the ResNet. So they show, okay, if they use vision transformer S with 16, generate bad performance. And this is CLIP. CLIP is a method developed by OpenAI. Okay, and there are also many different configurations. So what is the best configuration? It means they use CLIP vision transformer as their visual encoder. CLIP is a algorithm. It means you have a lot of paired training set. It paired means one is image, another is text. So you train two encoders, one for image, one for text, and try to convert those vector, I should say, visual vectors in the same space so that they can associate an image with a text or description. So they need a vision encoder. So they try vision transformer and try ResNet. They found if they use vision transformer, its performance is better than the ResNet. So here, the message is, okay, vision transformer become the state-of-the-art image classifier for many vision tasks. And then in our textbook, it talks about the application of image classification. He showed us an example. This is the Grok Neck, and it is a product of Facebook in 2020. It means given an image, it can recognize the object in the image so that it can sell or give the information to their advertisement buyer to promote their product to the customer. And okay, let's skip those details. And image classification, the easiest way you can try it is to use your cell phone. If you are using a Android cell phone, there is a app called Smart Lens. So if you use the Smart Lens, it will recognize the image you don't know. For example, this is flower, but you don't know it what the name of it. You can easily recognize it. And there is also a service provided by Google called Google Image. You can, for example, I don't know what the name of this bird is. So that I can upload the image, or just give Google Images the link, then it can classify this image and tell me the possible name of this type of bird. Okay, and then as we can see, there are many types of images, and the human faces is also a specific type of images. Face recognition, of course, it is a domain-specific image classification algorithm task. So for us human, our visual recognition system is very good. We can recognize images in very low dimensions. So this is the example given in our textbook. Can you recognize that? Some of them are very famous celebrities, but maybe 10 or 20 years ago. Okay, this is interesting. So how many people can you recognize? Yeah. Sure. So, yes, that's correct. Okay, let me show the answer. Yeah, number 4 is Clinton, correct. Yeah. Too young. Yeah. So I say this is the example given in our textbook. So when Selesky was reading this, okay. So when the paper was published, Tom Hanks was young. Okay, so there are many face recognition datasets. Okay, a lot of it, because we watch human faces every day. So this is interesting and important. There are a lot of applications for image facial recognition. Okay. So that's what I said. Remember, this is Mark Evergreen. He is the main organizer of the PET-scale VOC dataset, and he died unfortunately very young. So there is a Pammy Evergreen Prize every year. This year, this prize is awarded to the team of a Celeb A dataset. Celeb A is a human faces dataset. It was published in ICV 15, and there are 10K identities. All of them are celebrities. And there are 202K face images, along with some labels, including the landmark localizations and attribute. Okay, so this is project started by my computer vision students. So they want to classify images under the extreme lighting condition. So this example, but however, they didn't generate a very good result. And this is a research topic. That's fine. And let's take a look of some famous face image dataset. So this is a CGU multi-pi. CGU is Carnegie Mellon University. Okay, multi-pi means there are different poses, illustration, and expressions. So given this example, this is different poses, and this is different illustration. You can see this is brighter on the left side and the brighter on the right hand side. And the season means they took those images on different reasons. There is a gap. They want their images has certain variety. And they also provide a high resolution image and expression. So this is the cry and this is a smile. Okay, this dataset is well organized and very large. It takes around 300 giga to store all of those images. Not only images, there are also videos. Okay? But the only problem is Okay, when my student asked me, where can I get the multiply data set? And they finally found it is not free public available. If somebody want this data set, they need to pay for it. But however, Syllable A is totally free. So that is the advantage of this data set. Okay. So this is why the Syllable A contribute significantly to the computer vision community. So let's take a look how the multiply dataset was compiled. There is the studio in Carnegie Mellon University, and there you can see there are 15 cameras. When the subject is sitting on the chair, there are 15 cameras and 18 flash lights. So they can control those devices to take images at the same moment. So they can create a data set with different poses and different illumination. So if we can correctly classify images, there are many applications. One of them is the facial manipulation. Okay, and yeah, so this is example. They collect, so this is a very old paper published in 1995. They compile a dataset with 61 female and 41 male human faces, and compute their mean of those images per gender, and their shapes and their color difference. So this is very simple representation, only two factors. One is shape and another is color. So given an input image, okay, because there are two genders, they can move those the image presentation into the neutral. Neutral means the mean of the two genders. So from here and here, it's difficult to tell which gender the face belongs in, and also switch your gender from male to female, okay, and enhance the appearance of a gender. So from here, so what you can see, what is the for male, there are for female, the color on the lip and on the cheek is more significant than female. This is much redder. Okay. And how to model human faces? One straightforward way is just reduce the dimension. Use the eigen. Okay, it means given a face image, just think it is a vector. How many pixels are on the image? Just treat that as an element of a very, very long vector. When we have a very, very long vector, how to their distribution? Their distribution may look like this one. So, however, this is illustration because this is a two-dimensional figure, and for an input image, then the vector, the length of vector is always several hundred. Okay, however, we can use the principal component analysis. It means to find the most significant direction among this distribution. In this case, it will be this one. Okay. So given a lot of human faces, it looks like there will be a lot of sampling point in their spaces. Then they can, after finding the principal component, they can project the input image into those components. So this is the first component of the eigenface, the second, third, and fourth. So that they can use those facial faces. It means if they can just record the coefficient of those projected project, so that what they can, I should say, reconstruct or represent the human face so that they can do face recognition or face detection, etc. And there is another way to model human faces. It very famous one. It's called active appearance model. It means find the key point on human faces. So this is the example. They find the key point along the shape and on the lips, on the nose, around the eyebrow. Or if so, what they can do? Suppose they have only 420 images. That said, they can find the principal component or the most significant direction among the 420 images. Because why? 420 images means 400 sampling points in the 68-dimensional space. Therefore, they are like this one. Of course, there are some distribution, and then once they can find what is the important vectors or important orientation among the distribution, they can move. As you say, move the image along this diagram. So let's see. The center of the four set of images is a neutral, and if they move these images along the first direction, then so this is the mean, and this move it to the 3 sigma. Sigma means the standard deviation. You can and this is the opposite direction. So what do you see from here? I think along this direction, it will be the orientation of the face. So here it is a neutral, and this is moving slightly left, and this is moving slightly right. And this is the second axis. So from the mean to this one and to this one, what do you think? I think along it is the depth, I should say the height of the face. This is longer, and this is the shorter. And what is the axis? I'm not sure. I don't know what is the axis means. And what is the axis? I guess this axis presents the width of the eyes. So here the width of the eyes, the height of the eyes is much narrow, and this is larger. So this is how to present the face images. And of course, this is for 2D, and it is easily extended to 3D. If you so as you can see, this is the paper. The method was published in 2001, and it is 2007. 6 years later, they try to deal with the more challenging. And so this, in their paper, they propose the 3D. So this is a AAM model. This is a 3D AAM model. And so they can use several iterations to match those key points in the 2D faces, and also estimate the orientation. So once the mesh can be well estimated, then they know the orientation of the human head. So deep face, as you can see, from 2012, the AlexNet was released. Here, from 2012, the AlexNet was released. The power of neural network has been quickly spread out the whole community of computer vision. Everybody want to try. How can they use neural networks to deal with their existing problem? So in 2014, the first facial recognition algorithm using neural network for face recognition was proposed. It only consists of 9 layers. In 1912, the AlexNet only used 5 layers. So they modify AlexNet and extended to 9 layers. And but however, the most significant one is they need a lot of face images. There are 4.4 million face images. So who can collect so much face images? So let's take a look at the table again. Okay, so so there are. So for this data set, there are only 30K images, face images, and there are only 30K. And mega face, it was the state of very famous data. There are only 1 million data set. So which you guess who can get 4.4 million faces in 2014? Facebook. That's right. Facebook almost had so many faces in that year. Because there are so many users of Facebook, and they upload a lot of images to Facebook. So this is the approach. First, they will detect the faces, and then they will crop it. Then use the AM model to localize the key points of the faces, and then apply their 3D model. So this means convert the 2D model into 3D. So they can estimate the match of each triangle. Then they converge, because in the face in the white, they can be any orientation. It will be difficult to classify them if they under those variety cases. So they convert the faces to turn it to upright down, upright frontal. So this becomes the upright frontal of the input face. They didn't use this step. I show here because it is part of our textbook figure. Until step G, they get what they want. Then they can, as we say, neural network is a function. So they need the unified input. The unified input is the face G. Then they once get the unified input. The resolution is also predefined, 152 by 152, 3 channels. Then go through their network, and finally they will create a vector of a number of among 4,030 people. So let's take a comparison again. Because this is a classification problem, so finally they need the score for AV class. So here they have 4,030 classes according to their definition. And in our image ISL challenge, there are only 1,000 classes. And so the output of those networks are a vector of here 1,000 values. Here again also 1,000, and here they increase the number to 4,030. In addition, so actually, deepface is the first method using neural network for face classification problem. And after deepface, there are a lot of algorithms. VGG face, from the name, you can know it's used the VGG network rather than the AlexNet network to deal with the same problem. The FaceNet, OpenFace, DeepID, etc. And currently, if you are interested in this problem, oh, I should say, if somebody is interested in problem, they can easily use a package called deepface. Some people organize those algorithms into a single package, and it is very to use. And however, the research is keep going on, and from a relatively new paper in published 3 years ago, as you can see, there are many methods. The first one is the deepface, published in 2014, and this is their accuracy, 97%, and a lot of new method was published, and their accuracy keep increase almost around 100%. And what's the I should say improvement of those different methods? Even though all of them use neural network, of course, they can increase. They can apply state of the art or better perform neural network. Just as we can see, there is a ResNet, and there is a ResNext, and there is a SENet. Also, there is an EfficientNet. There are many choices they can try, and they can also tune different losses. In the beginning, this is the softmax losses. This is the simplest one. It means, given we will have 4,030 output values, and they will convert those values into the probability of the whether the faces belong to a person. So the ideal case would be, okay, if this is a face of a person movie star, and the probability should be 1. And for all of other probability values should be 0. If it is not the case, then it will generate a loss. The loss will call the softmax loss. Of course, they can change the loss. They can change it to some other types of mathematical expressions. Once they change it to the contractive loss, okay, they will generate some better performance. And the triplet loss, it means they need for every image, they will create a vector in the feature space. They can compare whether if there are 3 vectors, and we know the 2 vectors belong to the same movie star, and the remaining one is not, then we can set a loss. It will penalize it. If the positive vector is far away from the anchor vector, and the negative vector is close to away. So for this case, we will penalize, and we hope our network will generate the vector so that if the anchor and the positive belong to the same person, okay, their distance will be relatively small. And if they doesn't belong to the same person, their distance should be quite larger. So there are different losses are used for face recognition. So that they create a new algorithms and which generate better performance. Okay, now I want to talk about the medical image classification. So this is the paper released by our this is a Dr. Zheng Qitong. You know it, right? Because he is our associated professors. Okay. And this is, you can download his paper from this link. Okay. And what he want to do is, given an image, X-ray image, he want to know whether there is a fraction in the image and where the fraction is. So for this column, yeah, there is fraction and he label then use the white arrow, and this is the heat map, and I want to show how to do it. Okay, so that's his motivation. And let me remind you first, this paper was published in 2019, and in that year, okay, as we can see the history, CNN also the paper was published in 2019, but the research get started in 1917. So in 1917, CNN outperforms humans for image classification. Okay, so they want, and human makes mistakes. So there are a diagnosis rate around 7% to 14%. So they want to know, can they use any existing CNN-based method to predict the actually it's an application. Use some existing classification algorithm and try their own data set to see how the algorithm will perform. Okay, so first they need a data set. How do they get the data set? From CGU Memorial Hospital. So they compile 25K image. Okay, but they are not the pelvic. This is the from wrist, the body. This is the torso part. Okay, and then their pelvic images, they are only 36K. Okay, and yeah. Okay, sorry, I run out of time. Let's stop here and let's continue to next week, right?